Hey there, and welcome. Have you ever looked at a building going up, just a skeleton of steel beams, and really wondered about it? Well, today, we're pulling back the curtain on one of the most brilliant ideas in all of engineering. It's a secret that's literally hiding in plain sight. So here it is, the big question. You see them everywhere, right? In buildings, bridges, overpasses, these massive steel beams, all shaped like a capital I. Why that shape, specifically? I promise you, it is absolutely not an accident. It is pure engineering genius.
The answer isn't just about saving a bit of steel. It's about using that steel in the absolute smartest way possible to get incredible strength. And to really get it, to crack this code, we need to wrap our heads around two key geometric ideas that engineers live and breathe by every single day.
Okay, so our investigation starts with a concept called the centroid. See, before we can figure out how a shape resists being bent, we've got to find its center, its perfect geometric balance point.
So what is the centroid? Well, it's actually pretty simple. It's just the geometric center of any flat shape. Think of it like this. If you cut that shape out of cardboard, the centroid is the one exact spot where you could balance it perfectly on the tip of your finger. For a beam, that point creates a line, the neutral axis, and that's where all the bending action happens.
Right, so finding that balance point, the centroid, that's step one. We know where it bends. But the real question, the important part, is how well does it fight against being bent? And that brings us to the main event. And this is it, a concept called area moment of inertia. Now, I know that name sounds super technical and intimidating, but stick with me. This is basically the mathematical measure of a shape's superpower, its built-in resistance to bending. And hey, don't just take my word for it. Here's a great definition from our source material by author S.K. Mondal. He calls it the basis of strength of materials. So yeah, this isn't some minor detail. This is the absolute foundation of structural engineering. Let's just boil it all down. Area moment of inertia. Let's just call it I for short. It's basically a stiffness score. That's it. A shape with a low I value, it's going to bend easily. But a shape with a high I value is incredibly rigid. So the goal is always simple. Get that number as high as you possibly can. And this visual just shows it all perfectly. It's not about how much material you have, it's about where you put it. Look at the flat rectangle on the left. All its material is bunched up close to that balance point, so it's floppy. But on the right, we took the exact same rectangle and just stood it up. Now, most of its area is far away from the center, and suddenly it's incredibly tough to bend. Now, the math behind this is where it gets really cool. For a rectangle, the formula has you multiply the base times the height cubed. Cubed! That's the secret sauce. It means a shape's height is way, way more important than its width. If you just double the height of a beam, you're making it 8 times more resistant to bending. That is just a massive difference. Okay, so we have our tools now, right? We know about the balance point, the centroid, and we know the big secret. Push your material as far away from that centroid as you can to get a huge moment of inertia, a huge resistance to bending. So, let's put it all together. And here it is, the aha moment. The I-beam is shaped this way for one simple, brilliant reason: to maximize its moment of inertia. It carves out all that lazy material near the middle where it wasn't doing much good anyway, and it concentrates it in the top and bottom parts, the flanges, as far from the center as possible. And, even though the shape looks a little complex, the way engineers figure out its strength is actually pretty straightforward. They just break it down into 3 simple rectangles: the top flange, the middle bit they call the web, and the bottom flange. Then they just add up the superpowers of each part to get the total strength of the beam. This right here, this is the payoff. This comparison shows you exactly how powerful this idea is. Take the same amount of steel, same weight, same cost, and shape it into a solid square versus an I-beam. The difference is just staggering. The I-beam, just because of its shape, has an extremely high moment of inertia. Its bending resistance isn't just good, it is absolutely exceptional. So there you have it. Mystery solved. The I-beam gives you the most bang for your buck, maximum possible strength with the minimum amount of material. And wait, it's lighter, it's cheaper, and it's incredibly strong. That, my friends, is what you call brilliant, elegant engineering. But here's the thing. This idea is so much bigger than just I-beams. Once you really get the concept of moment of inertia, you start seeing it absolutely everywhere. I mean, just think about it. The chassis of your car, the wings of a plane, the hulls of giant ships, even the bones in your own body are basically hollow tubes. Why? To place their mass far from the center to resist breaking. Nature figured this out millions of years ago, and we use the exact same logic to build our modern world.
And that's really why this matters. Learning this stuff isn't just for an engineering exam. It gives you a new way to see the world around you. You can start to appreciate the invisible, clever logic that's holding everything together, keeping us safe, and making our world work.
So the next time you drive over a bridge or look up at a skyscraper, you'll know the secret. You'll see the I-beam and you'll get it. And that kind of leaves you with one last question, doesn't it? What other hidden principles are out there, quietly and brilliantly shaping the world we live in every single day?